Welcome, everyone. This is part 5 in our series on analysis methods in NLP. We're going to be talking about feature attribution methods. This is fundamentally a powerful toolkit for helping you understand how the features in your model contribute to its output predictions. Our fundamental question here is kind of, why does your model make the predictions that it makes? There are many motivations for asking this question. Here are just a few. To start, you might just want to understand whether your model is systematic with regard to some specific linguistic phenomenon. Has it actually captured that phenomenon? You might also want to know whether it's robust to minor perturbations in its input. You might use these techniques to diagnose unwanted biases in your model, and relatedly, you might use them to find weaknesses in your model that an adversary could exploit to lead your model to do really problematic things. Fundamentally, I think that this is a toolkit that will help you write really excellent analysis sections for your paper. To that end, I'm going to try to show you a bunch of code that will help you get hands-on with these techniques. I'll do it at a kind of high level in the screencast, and I've just contributed this new notebook, Feature Attribution, to the course code repository, and that should be flexible and adaptable and help you take these techniques and apply them to whatever models and ideas you're exploring for your projects. The star of our show, really the only reason that I can do this, is this amazing Captum.ai library. It implements a wide range of feature attribution techniques. We're going to talk extensively about the integrated gradients method and use the gradient-based method as a kind of simple baseline for that method. But as you can see here, Captum implements a wide range of different algorithms, some very particular to specific model designs, and others completely agnostic about what kind of model you're exploring. So it's a very exciting toolkit. The Sundararajan et al. 2017 paper introduced the integrated gradients method. It's also a lovely contribution because it gives us a kind of framework for thinking about feature attribution methods in general. And as part of that, they offer 2 axioms that I'm going to use to guide this discussion. The first and the more important one is sensitivity. If 2 inputs, x and x prime, differ only at dimension I and lead to different predictions, then the feature associated with that dimension must have non-zero attribution. And with my simple example here, you can get a sense for why sensitivity is such a fundamental axiom. If for some model M and 3-dimensional input 1, 0, 1, we get a prediction of positive. And if for that same model, the input 1, 1, 1 leads to the prediction negative, then we really ought to expect that the feature associated with the second position must have non-zero attribution because it must be decisive in leading the model to make these 2 different predictions. The second axiom is going to be less important to our discussion, but it's nonetheless worth having in mind. It is implementation invariance. If 2 models M and M prime have identical input-output behavior, then the attributions for M and M prime are identical. This is really just saying that the attributions we give should be separate from any incidental differences in model implementation that don't affect the input-output behavior of that model. To start our discussion, let's begin with this simple baseline, which is simply multiplying the gradients by the inputs. This is implemented in Captum as input by gradient. Here I'm showing with respect to some particular feature I, given model M and input X. And we simply get the gradients for that feature and then multiply it by the actual value of that feature. It's as simple as that. Here are 2 implementations. The first one in cell 2 does this for kind of using raw PyTorch, just to show you how we can use PyTorch's autograd functionality to implement this method. And the second implementation is from Captum and is probably more flexible, and it uses this input by gradient class. To give you a full illustration here, I've just set up a simple synthetic classification problem using scikit tools. My model will be a torch shallow neural classifier, which I fit on that data. And then in cells 9 and 10, I use those 2 implementations of this method. And you can see in 11 and 12 that they give identical outputs. Another thing worth noting here is that I have used the method by taking gradients with respect to the actual labels in our data set. You can often get a different picture if you take gradients with respect to the predictions of that model. And that might give you a better sense for why the model is making the predictions that it makes. In this case, since the model is very good, the attributions are only slightly different. That's our kind of baseline. I want to show you now that the input by gradients method fails the sensitivity test. And this is an example from the Sundararajan et al. Paper. They give this simple model M here, which is effectively just rel-u applied to 1 minus the input, and then you take 1 minus that rel-u calculation there. And that's the model. It's got one-dimensional inputs and outputs. If you calculate for input 0, you get an outcome of 0. And if you give the model input 2, you get an output of 1. Since we have differing output predictions, sensitivity tells us that we have to have differing attributions for these two cases here, these two one-dimensional inputs. But unfortunately, when you calculate through with this method, you get 0 attribution in both cases. That's a failure of sensitivity and points to a weakness of this method. Let's move now to integrated gradients. And let me start by giving you the intuition for how this method is going to work. Imagine we have a simple two-dimensional feature space, feature x1 and x2. So here's the actual point represented here. The idea behind integrated gradients is that we're going to compare that with respect to some baseline. And a typical baseline for us will be the all zeros vector. And then to do the comparison, what we'll actually do is interpolate a bunch of points between that baseline and our actual input, take gradients with respect to each one of them, and average all of those gradient results. And that will give us a measure of feature importance. Here's the calculation of the method in full detail. I've taken this presentation from this really excellent tutorial from TensorFlow Integrated Gradients. And it does all these annotations that I find quite helpful. Here's fundamentally how this works. The core thing is in purple. We're going to interpolate a bunch of different inputs between that baseline of all zeros and our actual input. That's what's happening here. And we'll take the gradients with respect to each one of those, with respect to each one of the features. And we're going to sum those up and average them. And that gives us the core calculation here. And then in 5, we just kind of scale that resulting average with respect to the original input to put it back on the same scale. And as I showed here, integrated gradients obeys the sensitivity axiom. Let's go back to that original example of a simple rel-u-based model presented here. I showed you that the input by gradients method failed sensitivity for this model. Integrated gradients, of course, is sensitive in the relevant sense. And you can kind of see why that's happening, because our core calculation now is not with respect to a single input in the case of the input 2, but rather with respect to all of those interpolated feature representations. Although some of those interpolated feature representations give a gradient of 0, not all of them do. And the result, in effect, is that you'll get a feature attribution of approximately 1 for this case of an input 2. The desired result showing sensitivity because, of course, the input of 0 in this case will give an attribution of 0. Now let me walk you through a few examples that show you how you can use CAPTM to get hands-on with the integrated gradients method. I'm going to do that for 2 classes of model. The first one is just a simple feed-forward network. And what I'm doing is reconnecting with the Stanford sentiment tree bank that we used during our sentiment unit. So on this slide, I've just set up an SST experiment using sst.experiment from that SST module. My feature representations are going to be essentially a bag of words, and I've filtered off stop words to make this a little more interpretable. And our classifier is a torch shallow neural classifier. I run the experiment, and a lot of information about that experiment, you'll recall, is stored in this variable experiment. Here I extract the model from that experiment report. And here we get a bunch of other metadata that we're going to use to run the integrated gradients method. The feature representations of our test examples, the actual labels, and the predicted labels, along with the feature names. And the one thing to note here is that for the sake of CAPTM, we need to turn the string class names into their corresponding indices, and that's what's happening in cell 9 here. Then we set up the integrated gradients using the forward method for our model. And we set up the baseline, which is that all zeros vector. And then finally use the attribute method. And here I'm taking attributions with respect to the predictions of the model. I think this can be a powerful device for doing some simple error analysis, and that's what I've set up on the slide here. I've offered 2 functions, error analysis and create attribution lookup, that will help you understand how features in this model are relating to its output predictions. You can see in cell 14 here, I'm looking for cases where the actual label is neutral and the model predicted positive. We can find those attributions, and this is actually an informative picture here. It looks like the model has overfit to features like the period and the comma, those ought to be indicative of the neutral category, but here it's using them in ways that lead to a positive prediction. So that's something that we might want to address. And we can go one level further if we choose and look at individual examples. So here I've pulled out an individual example. No one goes unindicted here, which is probably for the best. This is a case where the correct label is neutral and our model predicted positive. And I think the attributions again help us understand why, because by far the feature with the highest attribution is this best one. And this is revealing that the model just does not understand the context in which the word best is used in this example. That might point to a fundamental weakness of the bag of words approach. For my second example, let's connect with transformer models, since I assume that a lot of you will be working with these models. And these present exciting new opportunities for feature attribution, because in these models, we have so many representations that we could think about doing attributions for. Here's a kind of general picture of a BERT-like model, where I have the outputs up here. You have many layers of transformer block outputs. Those are given in purple, then probably an embedding layer in green. And that embedding layer might be itself composed of like a word embedding layer and a positional embedding layer and maybe others. All of these layers are potential targets for integrated gradients, and cap them again makes that relatively easy. So to start this off, I just downloaded from Hugging Face a Roberta-based Twitter sentiment model that seemed really interesting. And I wrote a predict1 proba method that will help us with the error analysis that we want to do. This next step here does the encodings of both the actual example using the model's tokenizer, as well as the baseline of all zeros that we'll use for comparisons. In cell 7, I've just designed a small custom forward method to help cap them out, because this model has slightly different output structure than is expected. Here in cell 8, we set up the layer that we want to target. And as you can see, I'm targeting the embedding layer, but many other layers could be targeted. Captain makes that easy. For our example, we use this is illuminating, which I'll take to have true class positive. We do our encodings in cell 11 of both the actual example and the baseline, and then that's the basis for our attribution of this single example. Now, for BERT, because we have high dimensional representations for each one of the tokens that we're looking at, we need to perform another layer of compression that we didn't have to for the feed-forward example. As you can see here, the attributions have, for one example, dimensionality 6 by 768. This is one vector per word token. To summarize those at the level of individual word tokens, we'll just sum them up and then z-score normalize them to kind of put them on a consistent scale. So that will reduce the attributions down to 1 per subword token. And that feeds into our final kind of cumulative analysis. So we'll do the probabilistic predictions, we'll get the actual class, convert the input to something that Captum can digest, and then use this visualization data record method to bring this all together into a nice tabular visualization. And that's what's happening here. You can see for our example, we have the true label, the predicted label with the associated probability, and then the really interesting part, per word token, we have a summary of its attributions. And you can see that green is associated with positive, white with neutral, and red with negative. And this is giving us a reassuring picture about the systematicity of these predictions. It's a positive prediction, and most of that is the result of the word illuminating and the exclamation mark. And that kind of feeds into a nice kind of error analysis / challenge analysis that you can do of models like this using Captum. For this slide here, I've posed a little challenge or adversarial test to see how deeply my model understands sentences like they said it would be great and they were right. You can see it makes the correct prediction in that case, and when I change it to they said it would be great and they were wrong, it predicts negative. That's reassuring, and so are the feature attributions. It seems to be keying into exactly the pieces of information that I would hope, and even doing it in a context-sensitive way. For the next two examples, I just change up the syntax to see whether it's kind of overfit to the position of these words in the string, and it again looks robust. They were right to say that it would be great, prediction of positive. They were wrong to say that it would be great, prediction of negative. Very reassuring. As is the second to last example, they said it would be stellar and they were correct. The only disappointing thing in this challenge problem is for this final example, it predicts neutral for, they said it would be stellar and they were incorrect. And the attributions are also a little bit worrisome about the extent to which the model has truly understood this example. Maybe we can think about how to address that problem, but the fundamental takeaway for now is simply that you can see how you can use feature attribution together with challenge examples to kind of home in on exactly how systematic a model's predictions are for an interesting class of cases.